Welcome to our lecture on integration by substitution. Today we are going to learn one of the most powerful techniques in calculus. If you have ever looked at a complicated integral and felt completely stuck, this is the tool that will save you. Let us dive in and see how we can turn messy problems into simple ones. Before we look at any equations, let us understand why this concept matters. Imagine traveling to a foreign country. Calculating costs in a foreign currency can be overwhelming, so you substitute it for your home currency to make the math easy. Integration by substitution works exactly the same way. In calculus, when an integral looks too ugly or complicated in our original variable x, we trade it for a new, simpler variable, usually called u. Mathematically, this method reverses the chain rule. We look for a messy, nested function, call it u, and watch the rest of the complicated expression simply disappear. Now that we understand the idea of currency exchange, let us look at how it works mathematically. This formula comes from reversing the chain rule. On the left, we have our complicated integral. The function g of x is our inner nested function, which we will replace with our new variable u. Right next to it is g prime of x, which is the rate of change or derivative of that inner function. This is the perfect setup. When we switch to the u world on the right side, the entire integral simplifies to just f of u. Notice that our starting and ending points, a and b, must also be converted into the new currency, becoming g of a and g of b. Before we prove why this formula works, let us see it in action with a concrete example. We are given a definite integral from 0 to 2 of 2x times e raised to the power of x squared. We want to find the area under this curve. This looks intimidating because x squared is trapped inside the exponent. But notice that the derivative of x squared is exactly 2x, which is sitting right next to it. So, we choose our inner function x squared to be our new variable u. Taking the derivative gives us du equals 2x dx. This means the entire messy chunk of 2x dx can be perfectly replaced by a simple du. We are continuing with our exponential example. Now that we have our u and du, we must convert our limits of integration from the x world to the u world. We plug our old lower limit, x equals 0, into our substitution equation u equals x squared. This gives a new lower limit of 0. We do the same for the upper limit, plugging in x equals 2, which gives us 2 squared or 4. Now we have all the pieces. We rewrite the integral completely in terms of u. Look how simple it has become. We just need to integrate the basic exponential function from 0 to 4. Let us finish solving our simplified integral. The antiderivative of e to the power of u is simply e to the power of u. Using the fundamental theorem of calculus, we evaluate this from our lower limit of 0 to our upper limit of 4. We plug in the upper limit to get e to the fourth power and subtract the result of plugging in the lower limit, which is e to the power of 0. Since any non-zero number raised to the power of 0 is 1, our final answer is e to the fourth power minus 1. This represents the exact physical area under our original complicated curve. Let us look at what just happened visually. On the left, you see the graph of our original complicated function in the x world, with the area shaded in blue from 0 to 2. On the right is our new, simpler exponential function in the u world, shaded in green from 0 to 4. Even though the shapes of the curves are completely different and the widths of the intervals have changed, the total shaded area is exactly the same. Substitution stretches or compresses the horizontal axis while adjusting the height, perfectly preserving the total area we are trying to calculate. Let us try another example, this time using trigonometry, which is very common in physics and engineering. We want to evaluate the integral of cosine x multiplied by sine squared x from 0 to pi over 2. Here, the sine function is squared, making it our inner nested function. Conveniently, the derivative of sin x is cosine x, which is sitting right next to it in the integral. So we choose u to equal sin x. Taking the derivative gives us du equals cosine x dx. This perfectly matches the remaining part of our original integral, setting us up to eliminate all the complex trigonometric terms. Continuing with our trigonometric integral, we must update our boundaries. We convert the lower limit by taking the sine of 0 radians, which is 0. For the upper limit, the sine of pi over 2 radians is 1. Now we rewrite the entire integral. The sine squared x becomes u squared, the cosine x dx becomes du, and our limits change to 0 and 1. Our complex trigonometric problem has transformed into a basic polynomial integral of u squared. This is the magic of substitution, turning a difficult problem into one you can solve in seconds. Let us find the final answer for our simplified polynomial integral. Using the power rule for integration, we add 1 to the exponent and divide by the new exponent, giving us an antiderivative of u cubed over 3. We evaluate this from 0 to 1. We plug in the upper limit of 1 to get 1/3 and subtract the result of plugging in the lower limit of 0. The arithmetic is very straightforward. The final answer is 1/3. This means the total area under our original trigonometric curve is exactly 1/3 of a square unit. Now that we have successfully used this formula twice, let us understand where it comes from and prove why it works. To prove the substitution theorem, we rely on the fundamental theorem of calculus. Let us assume that our continuous function f has an antiderivative called capital F. An antiderivative is simply a function whose derivative gives us back the original function. So capital F prime of u equals f of u. This is the core definition we need. Next, we will look at the composite function capital F of g of x, which means plugging our inner function g of x inside capital F. We continue our proof by finding the derivative of this composite function with respect to x. According to the chain rule, we take the derivative of the outside function, capital F prime, evaluated at the inner function, and multiply it by the derivative of the inside function, g prime of x. Because we established earlier that capital F prime is exactly our original function f, we can replace it. This gives us f of g of x times g prime of x. This is a crucial step. It proves that capital F of g of x is the exact antiderivative of the complex expression we started with. We are ready for the final result of our derivation. By the fundamental theorem of calculus, the definite integral of a rate of change is just the total change in its antiderivative. So we integrate both sides from a to b. The left side becomes a complicated integral. The right side becomes capital F evaluated at g of b minus capital F evaluated at g of e. But wait, this subtraction is exactly what we get when we integrate f of u in the u world from g of a to g of b. Since both integrals equal the same subtraction, they must be equal to each other. Hence, the substitution theorem is proved. We have covered the full topic of integration by substitution, and you have done excellently. Let us reinforce the most important ideas. First, substitution is your go-to method for simplifying complex integrals by replacing a nested function with a single variable, u. Second, it works perfectly when the derivative of that nested function is also present, because it is simply the chain rule in reverse. Third, and most importantly, always remember to update your limits of integration to match your new variable. This technique is not just a math trick, it is an essential tool used across physics and engineering to untangle real-world nested rates of change.